In the first half of this chapter, we talked about fossil fuels, including coal, oil, and natural gas, and we looked at some of the environmental impacts associated with their use. Now we're going to take a look at some other energy resources, both some non-renewable and renewable, what we would call alternative energy resources. The first of these is nuclear energy. Nuclear fission is what we have that produces nuclear energy. And what that means is we take the atomic nuclei of some fissionable material, and we'll talk about what those would be later, and we split those nuclei by bombarding them with neutrons. All right, so we're talking chemistry here. So we've got a nucleus and we bombard it with neutrons, and when that happens, there's energy released along with other neutrons. So we've got energy released in the form of heat as well as other neutrons. And then those neutrons that escape will then bombard other nuclei that are nearby, causing, again, energy to be released in the form of heat as well as other neutrons to be released. And so, as you can see, we see sort of a chain reaction beginning. We have neutrons bombarding a nucleus, and then more neutrons emitted, and then they continue on and bombard other nuclei. So this is how nuclear energy is created. We have a controlled environment where fission produces this heat, this energy in the form of heat, and we do so by bombarding nuclei. Now, the material that we use as essentially the fuel is some fissionable material, and uranium is the big guy. And uranium in nature, it exists in relatively small proportions. In the rocks, it's like there's two parts per million is sort of an average concentration, and that's really that's a low concentration. So if we actually want to mine uranium at a profit and use it for creating nuclear energy, it has to be 400 to 2,500 times its natural concentration. And remember, we call that a concentration factor. And so it really needs to be a pretty high concentration in order to mine it. So just every uranium we come across in nature, it's not going to fit the bill as far as what can be used for the fuel for nuclear energy. And most of the uranium that we find in nature is uranium-238, and that's like over 99% of the natural uranium. But and that is not fissionable. The only naturally occurring fissionable uranium we have is uranium-235, and that's a less than 1% of what we find in nature. But the uranium-238 that we said is a large percentage of the uranium, it can actually be converted into plutonium, which is fissionable. So if we bombard its nucleus with neutrons, then we actually do get fissionable plutonium. Here we have a diagram that illustrates sort of the chain reaction that we get. If you look on the left, you've got a little green neutron. And if we send that neutron toward the uranium-235, remember that's a naturally occurring fissionable material, the blue uranium-235 nucleus, you see it coming in contact, and then you see a lot of different things coming out of it. You've got the little green particles, which are more neutrons. Those neutrons are released from the nucleus. Those little green neutrons are going to go on to bombard the other blue nuclei that you see out there and cause a chain reaction. The reaction will continue. The other thing we see being released is fission fragments as well as energy. The little red squiggly arrows are representing energy that's released in the form of heat. And it's that heat, it's that energy that's released that we use to actually generate electricity and power. And so when we hear nuclear power plant, we're counting on that energy that's released in these sorts of reactions, that heat energy, to heat water, produce steam. The steam will then turn the turbines, and then we'll have power generated as a result. This is a schematic of a nuclear reactor, and this is the sort of construction that we would have to prevent an uncontrolled nuclear reaction from occurring, like we have if we're talking about bombs, for example. But that's a very different scenario from what we use in a nuclear power plant. You're going to have a very controlled environment. And so what you'll see are specific components. There will be essentially a core. The reactor core contains the uranium, a very concentrated segments of uranium to serve as the fuel. And then there will be some fuel pins. Those are the uranium, and then control rods. The control rods are sort of neutron collectors, if you will, and they're going to control how quickly the chain reaction takes place. So they're going to control how many neutrons there are doing the bombarding that we mentioned earlier. And so as the rods are inserted into the core, then they're going to slow down the reaction. But when they take the rods out of the core, when they're pulled out, then the reaction is going to speed up because there will be more neutrons available to continue that chain reaction. Then we have some form of coolant. Usually we're talking about water. And the coolant is going to take the heat away. It's going to take the heat that's being produced by the reaction away. And so as the heat's produced, it needs to be taken away at the same rate that it's being produced in order to maintain that equilibrium. We need to have the rates match, because if they don't, that's when we can have an accident. If heat builds up within the reactor core, that's when we can have a meltdown, what's referred to as a meltdown. And you've probably heard about meltdowns that have occurred in history because they're certainly very damaging to the community or the country even where they happen. And so they usually are big headlines. Fortunately, that doesn't happen very often. And as technology has improved, we're moving away from, or we're improving the technology to the point where it lessens the likelihood of that happening. So a meltdown is when we've got heat that builds up in the reactor core, and then when that happens, the containment fails, because this whole system, this reactor that we're looking at, this picture right here, this would be contained in stainless steel and then concrete around that. So it would be as contained as possible, because these are radioactive materials that we don't want in the environment. But when there's a meltdown, the real problem is the fact that the containment fails, and so you end up having the radioactive material getting out into the environment. So again, newer designs are implementing improved safety features, and so we really reduce the probability of a core meltdown. Here we see a comparison of fossil fuels and nuclear power plants, and the reality is the general idea is the same. We're burning some fuel when we talk about a fossil fuel power plant, whether it's oil or coal or natural gas. We're burning it, and then that is creating steam. The steam turns the turbine, which then sends out power. Okay, we convert that to electricity and send it out to the grid, to your house. And then with a nuclear power plant, the reaction is producing, the nuclear reaction that's taking place, that chain reaction we talked about, is producing the heat, and that heat is then whisked away. Like we talked about, we've got that coolant that's running through the reactor, and so that is carrying the heat away. And again, that heat is going to produce the steam. The steam is going to turn the turbine, and then again, we have the electricity produced. So same basic concept, just different mechanisms for getting there. There are risks associated with fission reactors, with nuclear energy, and often when you hear about nuclear energy, you'll hear about it. You'll hear about people being opponents of nuclear energy because they're worried about certain things happening. Particularly, they're worried about radiation getting out into the environment. Now, there's going to be some of that can't really be controlled. That is a part of nuclear energy. Any of that occurs with just the mining of the material and the transport of the material, that's sort of unavoidable, but that's not really the big concern. The big concern is if there were a meltdown. And so the accidents that I mentioned before that you may have heard of are the reasons that people are particularly concerned. And so I want you to check out a couple of examples. We've got 3 Mile Island, that is in Pennsylvania in the US, and then we've also got Chernobyl, that's former Soviet Union, what's now the Ukraine. So check those out in your textbook and read those case studies. they're not necessarily case studies like you've had in the book before. I think they're just contained within the discussion of nuclear energy. But take a look at those two, and that will give you an idea of why people are especially concerned. But like we mentioned, with new technology, there are measures taken to really reduce the chance of meltdown occurring. Um, there are other concerns though with nuclear energy. Another is, remember earlier I said that plutonium can be created when we bombard uh, the uranium 238, which is not fissionable in its naturally occurring state. But when we bombard that with neutrons, then the uranium 238 becomes plutonium, which is fissionable. And that plutonium that's produced by nuclear reactions in nuclear power plants, even that can be used in weapons, nuclear weapons. And so there's concern that put in the wrong hands, that can be used in a negative way. And then the last concern or a last concern, the last big concern with nuclear energy is nuclear waste. And this is a pretty solid concern because these are hazardous wastes, and we don't right now have a permanent, ready to go storage location that all the world is happy with for our nuclear waste. And we'll get more into talking about radioactive waste management in a later chapter. We're going to save that topic for another time, but definitely it is one of the big concerns with nuclear power. Right now, nuclear energy is about 20% of the United States electricity, so it is a bigger player, and United States does sort of want to see that expanded in the future. It does seem like a viable alternative, or one that should continue to grow. Um, there are definitely some benefits of it. It doesn't release carbon dioxide or cause acid rain. But there are the downsides, like we mentioned before. It does certainly produce hazardous nuclear waste and some other issues, concerns that go along with it. So we've talked about how nuclear fission can provide us with nuclear power plants and a pretty solid method of generating electricity for ourselves. But what about nuclear energy from fusion? Fusion is somewhat different from fission. Rather than bombarding a nucleus and splitting it into and having neutrons released from the nucleus, um, in the case of fusion, we have lighter elements that combine to produce heavier ones, and there's a release of energy associated with that. And the sun is the perfect example of a huge nuclear fusion reactor, as well as other stars. The problem is that nuclear fusion, in terms of our using this to produce energy for ourselves, is that it's really still a research objective. It is not something that has been developed to the point that it is a commercial reality that we can actually produce it economically and control the environment that we do it to where it's actually something usable. So it's sort of still a dream. Um, if we can get there, which hopefully one day we will, this would be a great source of energy because there is little radioactive waste associated with it. We have an unlimited supply of fuel to do it because hydrogen would be the fuel, and so this really would be wonderful if we can get there. But right now, it's not a reality. So nuclear fission is really all we have as an option right now. Geothermal energy is another alternative energy form, and this definitely has some geological context because this is taking hold of natural heat from the Earth's interior and using that to produce electricity for ourselves, or just as an energy source, as a source of heat. So the way geothermal energy works is that we have certain areas where the geothermal gradient is higher than average than other areas. And the geothermal gradient, everybody knows that if you were to dig a hole in the surface of the earth and go down deeper, deeper, deeper toward the core, we all know that it gets hotter and hotter as we go deeper and deeper. But in some areas, it gets hotter faster. So the temperature increases with depth at a much higher rate. And so that's what we call the geothermal gradient. Where the geothermal gradient is high is an area where we might consider geothermal energy as a source or as an alternative fuel source. So where do we find these areas? They are usually associated with tectonic processes, particularly at divergent and convergent plate boundaries. So where we have plates coming together or plates moving away from each other. So tectonic processes are influencing where we have a particularly high geothermal gradient. It's not surprising that we find a higher geothermal gradient in areas where we have volcanic activity, right? Think about that. That's the high heat source close to the surface. Here's a map of the United States showing the geothermal gradient, and you can see that the blue areas are 12 degrees per kilometer. The orange areas are 47 degrees per kilometer, roughly. So as we increase in depth, we increase in temperature by that much on average. And so certainly the orange and yellow areas are areas where we would have the highest likelihood, the best chances of putting in a geothermal power plant and being successful. This is a more detailed map of heat flow in the western United States. And you can see the different colors indicating a higher heat flow. And again, the orange and the yellow are going to be the highest rates where the geothermal gradient is the highest. And then you can also see there's black dots on this showing where there are power plants located. And so it's not surprising that most of those power plants are located in the orange colored areas that have the highest geothermal gradient, with a couple in the yellow areas, but certainly none in the blue or the green. Here's an example of a geothermal power plant that is a hydrothermal convection system. And what we have is we have that heat source. Remember, it's heat source from the Earth's interior, so essentially magma that has come up from the mantle. And you've got that heat source that's not very far beneath the ground. And we know that we have groundwater beneath the surface. We've already talked about that in this class. And so that groundwater is hotter than average. And so when we put a well down into the water and we bring that water up, the pressure is lower, and that water is converted to steam usually, and that steam is then going to be used to turn the turbines, power the power plant. And then the leftovers, if you will then be injected back down into the aquifer, back down into the rocks, so that it can then be heated again and used again. So it sort of follows a bit of a cycle. And then this is another example. Again, it's still a hydrothermal convection system, but in this example, we've got sort of a vapor-dominated scenario where, again, we've got that steam that's going to be produced. We're going to pull that material up. Then we're going to use the steam to turn the turbines, and then inject it back down into the groundwater reservoir. And here's an example of what a geothermal power plant might look like. This is one in San Francisco. In terms of environmental impacts, geothermal energy, it does have lesser impacts, but it still has impacts. There's still noise associated with it. It still emits gases, scars on the land when we construct the power plant. We're going to have a lot of hot water that's produced, and the water may be briny. It may be chemically different from typical water. It's hot. We've talked about thermal pollution before, and so we may have some impacts associated with the release of that water. So it certainly still has its drawbacks, but it is a pretty viable energy source, but it's definitely site specific. This doesn't work everywhere, um, and it's fairly expensive. It's not really on par with the burning of fossil fuels, but in an area where you've got a high demand and where you have a high geothermal gradient as well, it's certainly a viable energy source. Right now in the U.S., it's much less than 1% of our energy, so it's not a big resource for us, but it really does work in certain areas. It's definitely a viable source. So the first half of the chapter we covered fossil fuels, our biggest energy source right now. 90% globally of the energy that we produce is from fossil fuels. And then we've just talked about a couple of alternative energy resources that are non-renewable, nuclear energy and geothermal energy. And now we're to those renewable alternative energy resources. And these are all derivatives of the sun's energy. Essentially, the non-renewable resources that we've talked about already, we can't replenish those as quickly as we use them. But essentially, the sun takes care of that for us, and with this next group. And so these all are considered renewable energy resources. Don't think that means that they don't have environmental impact. A lot of times people assume that if it's renewable, then it doesn't impact the environment. That's not the case. It's just that it's a bit more sustainable in that the resource itself is still replenished by the sun. Here you see those derivatives of the sun's energy that we just mentioned. We've got wind, we've got solar energy, we've got hydropower, and biofuels. The use of alternative energy resources has really grown lately. We have been on the lookout for alternatives, for a way to reduce our reliance upon fossil fuels. And really, with alternative energy sources, we have to match the facility with the best quality for the source. So alternatives can't always be used everywhere. They're fairly location specific, and so as just like with geothermal energy, you've got to be in the right place to use it. Most of our alternative energy resources are that way. There are ideal locations. The first we'll talk about is solar energy, and you can have passive or you can have active solar energy. Passive, the example, it says P there, but passive, the examples would be the building overhang that is designed so that it keeps the sun out in the summer, but then lets some of the low angle light in the winter, and sort of reduces your cooling and heating costs that way. Or an absorbent wall, a heat absorbent wall that's built to absorb the sun's rays and reduce the heating costs in the winter. So you don't have to do anything. You don't need a motor to run them. You don't need a mechanism. You don't have to input any energy. Once they're there, they're just passive. And then on the active end, we've got something that requires mechanical power, requires a pump or something like that. And so we'll look at a couple of those. The first is a solar collector, and these would be like your panels, flat panels. They've got a glass plate over a black background, and there's some sort of fluid inside them that's heated, and then it's circulated. And then that is going to, again, that heat is going to be used to produce steam, to turn the turbines, to create the power, right? So we've got the power plant idea, same concept, but a different fuel. Another is photovoltaics, and these are used to convert sunlight into electricity using some sort of semiconductor. And so basically you get the electrons flowing, and essentially that is your electricity. So you get the electrons flowing out of the cell and then through the electrical wires. And the use of photovoltaics has really increased The use is growing at about 35% per year. Um, this is still an expensive technology, but the gap is narrowing between the cost of this, and the traditional energy sources. So we're definitely seeing a large increase in the use of photovoltaics. Here are some examples of solar collectors, what they would look like, and you may have seen these before on a rooftop somewhere. And here are some photovoltaics. So those look fairly similar. You may not be able to tell the difference um, just by spotting them. All right, another alternative energy resource that is renewable is hydrogen, and hydrogen can be used similarly to fossil fuels. And the example that you've probably heard of is a hydrogen fuel cell that would be used to produce electricity or power a car. You've probably heard of it in that context. And this is definitely a clean fuel. The burning of it produces water, so it's definitely a clean fuel. And this is something that sort of experimentation continues, research continues. Right now, we're not really there. We don't see this used. We don't see this used on a very large scale, but there are definitely communities out there that want to move toward using hydrogen. And so we'll see how that continues. But this is may be a viable resource for the future as experimentation continues and prices can go down for this technology. All right, water power. You've actually had a little taste of this just because of some of the discussion that you've already had. So water power, it's an ancient resource. They used water wheels back in Roman times, and we've talked already a little bit about hydroelectric power. That's where we've got a dam in place in a river, and that accounts for about 10% of the electricity in the United States. So hydroelectric power is a great resource for us. It's environmentally it's fairly low on the environmental impacts, but it's a great resource for us. And the problem with hydroelectric power is we can't really expect it to grow that much. Most of the big sites that are ideal for a dam have already been used. So we already have dams in those locations. And so there's few big sites left. So that 10% of our electricity in the United States, it actually may decrease over time as we bring in more alternative energy resources. And so it is a great alternative energy source, but we're fairly limited in how much expansion there can be. We may see some smaller scale projects put in, but again, if you have several of those, you still seem to get the impacts, and so who knows where that'll go. But we don't expect to see a whole lot more hydroelectric power plants put in the United States. Tidal power is one, again, very location specific. With dams, you got to have the right spot, you got to have the right scenario. Tidal power, again, you've got to have an area where you have a huge fluctuation in the tides to make it worthwhile, to make it something that's feasible. But that's another possibility out there. Environmental impacts. You guys actually did some research on this on your own, some of the disadvantages of dams, and so you've actually looked these up already. Okay, wind power is another alternative resource, and this is a pretty big one. This is a pretty hot one. It's evolved over time. The windmill, now when we hear windmill, we're talking huge wind turbine. We're going to call it a turbine now because it's massive, high tech. There are people whose job is to find the ideal locations for wind power. And it takes the right geology, it takes the right shape of the land, it takes the right spot, again, the right wind conditions to make a feasible site for wind power. Like I said, the windmills are massive and state of the art now. And so this is something that you've probably heard mentioned more in the last few years than you had previously. The environmental impacts are relatively low with wind power. This is a very fast, very rapidly growing energy source, like 30% increase per year. Um, Widespread, abundant, inexpensive, no air pollution. So again, the impacts are fairly low, but there are some hazards. We do have some environmental impacts. Nothing is without any impact, it would seem. Um, they do take up some space, not that much, but yes, windmills would take up some space. Not everyone likes the sight of windmills, so they would ruin scenery, if you will. Um, and then there's the birds. Sometimes you got a bird, he's focused on his prey, he's after it, he's not paying attention, and he comes in contact with a windmill. And it's not a good day for that bird. So, not everything about windmills is calm and serene and beautiful, but this picture would kind of suggest otherwise. So, we've got certain areas that have an increased wind resource. So, as we have air, wind, we will have more of a wind resource where we have, if we were to put a windmill at the top of a mountain or at the edge of the sea. We all know that. We've been to these places. Yeah, we've got more wind, right? A mountain pass where it gets narrow, right? We may have more wind. So there are certain areas, geologically speaking, that are ideal for wind power. Again, certain locations where wind is a better alternative resource than others. All right, one more alternative energy resource is biofuel, and this would include organic matter, plant material, animal waste. So we're talking about wood, burning wood for energy. This has been done for quite a while, right? And then animal waste, yeah, like livestock, dung. Did I really put dung on the slide? I did, but it's true. It's what it is. Primary sources in the United States would be forestry products, agricultural products, and then combustible urban waste is another example. So we're talking trash. But these are again an alternative fuel source. Now we're burning, and so we will have the release of some not so great particulate matter. But still, like we said, just because they're alternative resources doesn't mean they're without environmental impact, but they do tend to be a little lower. All right, when we talk about alternative energy resources, when we talk about energy development, where we're going in terms of energy, we have to look forward. We have to look into the future and keep these ideas in mind. It's just not practical not to. So the first is conservation. Can we adjust our uses so that we demand less energy? Can we keep a control on our energy demand? That certainly is going to help us move towards sustainable development. The second is efficiency. Can we revise the way we do things? Can we redesign? Can we work on new technologies, new equipment, so that we get more out of it than we do now? For the same amount of energy, we get more power. So that's the concept of efficiency, and obviously that's a goal as well. That helps us. And then cogeneration. This is a concept that you may not have thought about before, but can we capture and use waste heat? Okay. When we do something that consumes a whole lot of energy, usually in that process there's a lot of energy lost. Can we trap some of that energy? When I say energy, a lot of times we're losing it in the form of heat. Can we then take advantage of that heat? For example, if thermal pollution is an issue, if you have an industry that is releasing hot water, could they instead use that hot water to do something? Could they save some of that energy from their operation? And so this is the idea of cogeneration. Can we capture and use that waste heat? Let's talk for a minute about where we all use energy. because we certainly use a lot of it. We're responsible for those big numbers that we've talked about already in this chapter. So in our household, we're talking about when we use electricity, natural gas, propane, wood, wind, photovoltaic, whatever it is your house is run on. Probably the burning of fossil fuels, but it could be something else, depending on where you are. Transportation, we all know that we go to the gas station. That one we feel. That's the one that everybody likes to really complain about is the price of gas. But yeah, so we all consume fossil fuels in that way. And then purchases, when we buy things, every time you buy something, in a sense, you are buying some energy that has been transformed into that product. So to make every product that you buy, some energy was consumed. So you can also think about consuming energy that way. Every time we buy something, we're also in a sense using energy. So we said efficiency before was finding a new way to do something that uses less energy but yields the same thing. And the question here is, what if 3 quarts of milk were lost between the cow and the gallon jug that you see in the refrigerator, and you only got 1 quart? And the thing is, that's kind of how it is with electricity. The efficiency of the system from mining a product to getting it to the outlet, to the power coming through the outlet to your house, you're only getting about 25% efficiency. For every BTU that's delivered, 3 are wasted. And so we lose a lot in the process. And so we have a goal is to get to where we are more efficient with the way that we do things. An internal combustion engine, a car engine, works in the same way. The total efficiency is only about 20%. Even the really efficient car doesn't actually improve that much. It's still surprisingly low. I should check the number, but I think it's about 35% if you've got a really efficient one. So it's still not very high. If it was 20%, for every one delivered, 4 are wasted. So similar concept there. So certainly our standard of living is tied to our consumption of fossil fuels. And so our standard of living has environmental implications. We talked about some of those earlier in the chapter. There are different ways of thinking about energy in the future. Some would emphasize finding and using more fossil fuels, building larger power plants, making sure we've got plenty there and available and at a reasonable cost. And then there's others that might emphasize the energy alternatives a little bit more, those that are renewable, flexible, decentralized, and with fewer environmental impacts. But obviously that some of those ideas that we mentioned before, conservation, efficiency, cogeneration, these definitely need to be at the forefront of our minds when we think about where we want to move in terms of energy consumption. So, do we want to go in the direction of oil, natural gas, nuclear energy? Do we want to look toward wind, coal, energy efficiency, local production? Certainly. We talked about how some of those renewable resources are very location specific, but hey, if you've got the right location, what a great way to have another source. Energy efficiency, are we doing our part? Are we getting energy efficient appliances? They use less energy to do the same job. Is that something we're doing? The fluorescent light bulb is something that we've seen more and more of as time has gone on. In the past few years, you've seen them more and more at the store, on the aisle, and that's something that you can do. And that's good for you. It's not just good for the earth, but it's good for you as well. They don't burn out. You don't have to replace them. They burn out, but not nearly as quickly. They last much longer. You don't have to replace them as often, and they use far less energy. So you're going to see a decrease in your energy consumption when you switch to fluorescent light bulbs. So that's a pretty easy switch to make, in terms of what you can do fairly easily and without much cost. A little upfront cost, but the savings will follow.